So, as we proceed into the last section of this chapter, we're going to look very quickly at dihybrid crosses, which we ended the last section with. And just keep in mind that this is really where the principle of independent assortment came from. So, a dihybrid cross is actually looking at two traits. So, for example, in this figure, we're actually looking at the two parents, and they have two phenotypes. One for seed shape, it's either round or wrinkled, and one for seed color, it's either yellow or green. So, in our P generation here, our first parent is homozygous for both traits, so big R for round, and big Y for yellow. And our second parent is actually homozygous recessive for wrinkled seed shape, little r, and green seeds, little y. So as these alleles move from the parent generation into the first generation, we really only have one choice from each loci that each parent can contribute. So in this example, parent number one can only contribute a big R at the first loci for round seed shape, and can only contribute a big Y for yellow seed shape at the second loci. And respectively, we have the lowercase genotypes coming from the second parent in this situation. So that F1 generation, 100% ends up being round and yellow for the phenotype, but the genotype is 100% heterozygous, so big R, big Y. And as self-fertilization is able to occur in the F1 generation or among the F1 generation, then we get certain loci actually being able to transmit into the F2 generation. So we could have dominant genotypes for both parents sorting off. We could have recessive genotypes for both parents sorting off. We could have a heterozygous big R little y genotype separating off, or we could have a heterozygous little r big Y genotype sorting off for the F2. So our F2 generation has lots of possibilities. It's not just the simple 3-to-1 ratio anymore. So in this F2 generation, because we're dealing with two traits, our Punnett square actually gets a lot bigger. It more than doubles in size. So we go from 4 squares to actually 16 squares. And in typical classic Mendelian inheritance, a dihybrid cross for two traits that act in a dominant and recessive manner are always going to end up with a phenotypic ratio of 9:3:3:1. So in this case here, 9 genotypes are actually going to be round and yellow, 3 genotypes are going to be round and green, 3 genotypes are going to be wrinkled in yellow, and 1 genotype is going to be 100% recessive, and that's going to be wrinkled and green. So our dihybrid crosses, you know that you're dealing with a dihybrid cross if you see a phenotypic ratio of 9:3:3:1. So an easier way to actually figure out the percentage or the probability of a dihybrid cross is by using the branch diagram. And it's easier to use this branch diagram than it is to create like a 16 square Punnett square. That can get pretty confusing pretty quickly. So a branch diagram is where crosses can be broken down into two monohybrid crosses. So looking at the two traits individually. And then we can recombine those probabilities using the addition and the multiplication rule. So the branch diagram doesn't have any Punnett squares associated with it. So as we start to build this branch diagram, just keep in mind that we're looking at the two traits separately. So in this case, our first trait is seed color, and is seed shape, either round or wrinkled, and our second trait is going to be seed color. So in this example, if we have a heterozygous individual, so big R, big Y, and we cross it with another heterozygous individual, then we can actually break out the two traits. So if we look at shape first, we know that the parent is only going to be big R, and so the probability that they actually pass their traits on comes to a 3-to-1 ratio. So 3/4 of the offspring are going to be round, which means that they have the big R in at least one loci within their genotype. That's going to result in a round phenotype. And 1/4 of them are going to be homozygous recessive, meaning that they have a little r, and going to have a wrinkled phenotype. So if we look at the second trait separately, which is seed color, either yellow or green, we get the same relationship happening because we start off with a heterozygous parent genotype of big Y, and we would cross that with the second parent, which would contribute a big Y or a little y as well. So as we predict the probability of that, um, 3/4 of the individuals for the second trait, seed color, would be yellow. They're going to have that big Y in at least one location in the genotype. And then 1/4 of the individuals would be homozygous recessive, little y, or green. So we split up the two traits. We looked at seed shape first, and then we looked at seed color second. So as we then start to break down and branch this pattern out, we're going to look at this in terms of a column format. So our column or our trait that we're going to start with is seed shape, so round or wrinkled. We know that we're going to have a 3-to-1 ratio based on what we just talked about. And then our middle column is going to be the second trait, so seed color. So we know that if we have um, a round individual, they can either have a 3/4 chance of being yellow or a 1/4 chance of being green. So we end up multiplying across in this branch diagram to get our 9/16 or 9 out of 16 individuals that are going to be round for seed shape and yellow in seed color. And if we wanted to look at the proportion of individuals that were going to be round and green, we would then take our 3/4 individual, or 3 out of 4 individuals that would end up with a round phenotype, and multiply that by the 1 out of 4 individuals that would have the homozygous recessive green phenotype. So 3/4 times 1/4 equals 3 out of 16 individuals that are going to be round and green. So what you end up doing is actually just multiplying across. So you take your two chances or the two phenotypes that can show up in seed shape, and you're going to multiply them across for the two phenotypes that you can see in seed color. And that will give you, at the end of it, your 9, 3, 3, 1 phenotypes. So you get the same results as in the Punnett square. The branch diagram just breaks out a little more clearly. All right, so again, just keep in mind if you are working through a separate problem where you have a heterozygous individual, so a parent that is round and yellow, and you're crossing that with a parent that is wrinkled and green or homozygous recessive, you're going to look at those two traits individually. So first you're going to look at the round or wrinkled phenotype, and we know that um, the round or wrinkled phenotype is actually going to separate out into 50/50 phenotype. So half of the individuals are going to have a big R and be round, and half the individuals are going to be a little r and be homozygous recessive or wrinkled. So then if we look at that first characteristic, then we can split out our second characteristics as well for seed color. and we end up just multiplying across our two traits to get a branch diagram that ends up being a 1 to 1 to 1 to 1 ratio. So a quarter of the individuals with these parents are going to have the chance of being round in yellow, a quarter are going to be round in green, a quarter are going to be wrinkled in yellow, and a quarter of the offspring are going to be wrinkled in green. So again, it all goes back to what parent genotypes you start with. So as we extend out beyond 2 traits to 3 traits or even 4, our branch diagram gets a little bit bigger, but it's still much easier than trying to predict a Punnett square and match up all the genotypes in a Punnett square. So I encourage you to practice a couple of these branch diagrams just so you know how to look at individual traits and then multiply them across.